Hello and welcome to Lab 5, Magnetic Braking with Faraday. Introduction to this lab, we gain an understanding of how current can be induced on a ring and thus objects that can be equivocated to multiple rings. We also learn about the Lenz's law, the direction of negative magnetic flux to restore the initial state of the B field, and how objects can reach a constant velocity while falling. Some key concepts we have to understand, as I just mentioned, terminal velocity, when the net force is zero in both the plus and minus y directions, reaching constant velocity through Newton's third law, Faraday and Lenz's law for magnetic flux, the induction and the direction of current, and then with all magnets we need the Biot-Savart law. Preview of the results, our values for the bar magnet and the aluminum foil, the radius, the magnetic moment, the mass, and the experimental results we got in real life when we dropped the magnet. We used the magnetometer app to determine the north end of the magnet, used the phone to record the fall for accurate time measurements, and dropped it from the top of the tube, caught it, and recorded the time, and we repeated this 5 times. Here's all the code. We coded for flux, we created a loop, and we coded for the dipole moment on the starter code. Everything entered, and we got the results again, where we see on this graph the region where velocity is constant is the terminal velocity, and we can see the magnet falling through the tube, and we can see that it took 1.202 seconds. Some discrepancies between our computational model and our experimental value. Our computational model gave us 1.2, and our experimental value gave us 1.35 as the average time. This is likely due to a couple factors, which could include human error, dropping it, the timing difference, recording, rounding values, etc. But more likely it's due to the imperfect forces like air resistance, which can impact the system of the magnet falling through the tube and add to the magnetic force that's going against gravity and helping us reach the terminal velocity. Interpreting the simulation, the red current on the model represents the counterclockwise portion of the rings, and the blue represents the clockwise. Both of these work to slow down the magnet as it falls, breaking it. The currents would be flipped, but the magnet would still slow if we flip the direction of the magnet so that the south end was pointing towards the tube as we drop it. As I just mentioned, discrepancy between our computational and our actual experiment is human error, and as well as our difference in forces between the computational model and real life. And at the beginning and end, the forces are unbalanced, as we can see in this graph, where in the beginning, velocity is decreasing exponentially and then increases with the brake, and then at the end decreases as it exits the tube exponentially. However, in the middle, it is constant, as we just said, reaching that terminal velocity. For the what if questions, if the resistivity of the conductor were reduced as close as possible to zero, or if it was theoretically zero, there would be nothing stopping the flow of electrons, and they could flow infinitely fast, which would cause even more force in the positive y direction, and it could stop the magnet from falling through the tube altogether, since the force could get stronger than gravity, or it could at least slow it down to a much greater extent than it did in our real life. If there are holes or slots cut into the tube, this would disrupt the current flowing and the electron flow, since they can't jump gaps. It would be like if a switch in a circuit was open, and this would do the opposite, and the magnet would be able to fall much, much faster because the braking forces would drastically decrease. And that is the end.